opportunity to present this morning. I'll try to run through this pretty quickly. I know we want to spend more time in the after period, but I just want to say that it's kind of fun. I'm at a place that historically did not do a lot of sharing. And by the end of my career, I'm hoping we have changed that and turned some corners a little bit. Very much from a lineage that tried to do everything in-house, try to control everything yourself very clearly. So it's really impressive, just seeing Tor, your first slide with some of those models. It's really impressive to think how quickly we've moved. So this is my PhD dissertation from 1989, a plain strain finite element model of the rabbit knee. And I see little snippets here of stuff we do today, but it's barely comprehensible. And I have to say that the finite element analysis code we had was an open source product where I was editing the code to make it do what I wanted. So I just think it's amazing to think how far we've come in essentially 35 years and kind of how much capability there is. So there's challenges ahead, but look at how far we've come. This really stems from a 2022 sabbatical I did. And I will say that, again, I'm at an institution, I'm in a department of orthopedics and rehabilitation. And actually, sabbaticals are almost an unknown phenomenon. And I just thought it was really important before I finished my career to try to take on something like this. So it involved both the University of Calgary and the University of Eastern Finland. I say here, generous grants funded both stays, but also generous hosts made the stays valuable. So the first one was with Walter Herzog at the University of Calgary as the lead host. I'd like to thank him specifically here. Of course, the application was submitted, everything was accepted, no go. You may remember something was happening about that time. COVID set this thing back, and we finally made a go of it in 2022. And it was a really wonderful time. Obviously, any kind of collaborations that involve moving to another place, just kind of unique opportunities to get out and about, which is really wonderful. And then Rami Korhonen was generous enough to host me at the University of Eastern Finland. And for those who don't know, Rami actually spent a postdoctoral period in Calgary. So there's a real connection here that made sense. Again, with the little COVID dance to kind of delay things a little bit, but and some fun there in Finland, of course. So in the midst of that, we actually gave a presentation at the European Society of Biomechanics that I thought was kind of an interesting take on this. And I think of my group at Iowa really have taken very much we're in clinical orthopedics, so it's kind of a top-down or almost a reverse engineering approach where you take your general mechanical knowledge and use it to somehow make sense of clinical observations. And then not to denigrate anybody at all, but this is kind of the way I see Rami's group on that. There was very much bottom up building from basic physics principles, a forward analysis where you can estimate tissue level mechanics and modeled. And honestly, in a lot of environments, people then struggle to actually have an application. So I say this only because I'm in a place where patients come through every day and there's lots of opportunities to interact with the clinical orthopedics piece, but not as much on the basic development work. The leash is relatively short. So I think this is one of the challenges to address. And I just want to bring that out a little bit in a series of slides here. So this was the presentation, the title I gave at the ESB in Porto. And it was really then, I don't want to get into my science too much. Of course, I love my science, but Tom Brown was my predecessor at Iowa and my graduate advisor. And he was the Orthopedic Research Society president and made this statement that still rings true for me. If we're to realize the tremendous potential, we need to enthusiastically promote an equal partnership between orthopedic clinicians and scientists. Of course, that's a luxury coming from a department where we have scientists embedded with orthopedic clinicians, and I recognize that. And here is our team, a mixed bag of biologists, surgeons, and engineers working together, really committed to being together, exploring the work that was being done by different groups and trying to make it better. Met regularly. This is almost impossible to imagine very many places where you can make this work, but this is what we did at Iowa, and this was our model to look at post-traumatic osteoarthritis. And out of that came some work. I think the date, my screen is just slightly obscured. I see 2002 for this. So some of the early work we had done with what at the time I thought was almost a feasibility study to even think you could do patient-specific computational modeling. These fractures that we happen to have CT scans on after somebody tried to put them together. And if you look closely, you might see fixators holding the ankles or screws actually holding screws and plates holding these fractures together. And we developed what I at the time was a workflow. Now it's just trivial to think that people can generate stuff like this. And we called it patient specific, but it was really only patient specific in geometry because here we talk about a generic loading profile we were using that we took from the literature and we put together a series of loads in this ankle to kind of produce something. And of course, I was pretty impressed that I was able to make these models showing intact ankles on the right and fractured ones on the left and seeing differences in the contact stress profiles. So all well and good. That's useful. Maybe use that in larger numbers. In this case, it happens to be only 20 ankles, but we were able to demonstrate that contact stress was actually higher in the cases um, that had fracture that went on to develop post-traumatic osteoarthritis 2 years later. So this kind of has obviously some implications for treatment, and we're pretty happy with that. But we kind of hit a crossroads there. Um, we developed discrete element analysis methods. Again, we don't have to get into details here, but the basic idea was that finite element was almost too complicated in these problems to go all the way from basic imaging through to context stress estimates, which were the currency we were using. So we came up with an automated methodology. Problems like CT scans, the ankle's not actually in a load-bearing apposition. So how do you get it in a load-bearing apposition? Then you can do your discrete element analysis. We're actually the post-op CT scans are not really standard of care, it turns out. So you kind of don't have that input. We've recently developed weight-bearing CT scans as a way you might be able to bypass that. Of course, one of the nice things is you no longer have to automate or figure out how to align to a loaded pose because you obtained the image with it in a loaded pose. We've extended these methods to other joints and shown that it could be useful. This DEA is pretty straightforward, can run pretty quickly, et cetera. So that's an approach to maybe doing patient-specific numbers on a larger scale. So just a slight aside, I said there's some biology in that too, and these are some basic slides I borrowed from a paper back in 2011, but essentially identifying in the case of post-traumatic OA where there's something that initiates this process so we know exactly what we're trying to do. And there's a perturbation in the biology that in the mechanics that may be able to be addressed in a fairly direct method. We were working with the biology group. I just showed Rami and Petri might chuckle a little bit about this basic equation down at the bottom. We had toyed with the idea of doing some complementary mathematical or even finite element model to really get down to this mechanobiology. But I will say the biology is really impressive. In the course of my career of 35 years, biology has finally gotten to where they have quantitative output metrics that you really can compare your quantitative mechanical metrics against. Not getting into too many details here again, essentially showed that with an explant model, osteochondral explant model loaded in certain ways, you could look at the mitochondrial activity and showed real indications that oxidative stress might explain some of the biology of post-traumatic OA. Then come up with potentially some methods to address that oxidative stress. And I'll just say NAC was one of them. And this really put us at a point where you could imagine hundreds of these treatments that you could evaluate with biology. You'd be using animals till the cows come home literally to try to get somewhere. So clearly there's an opportunity here for math and computational modeling. We're able to show that NAC could actually disrupt this y-axis parameter that I don't even want to talk about, two different animal models here. So it really points towards a potential clinical therapeutic treatment, but who knows how to optimize that except a whole bunch of animal models. And then a group from University of Eastern Finland happens to reach out to me about that time. And I've put in a couple of their slides here. Thank you, Rami and Petri, for allowing me to show a few of these slides. But this bottom-up approach kind of appeals to me. And you're sitting here with the opportunity to look at specific models with specific anatomies, and even potentially looking at how cytokines and other actors in the body influence inflammation. I love Rami's little slide here. If you ask a biomechanist, it's chronic overloading. You ask a biologist, altered metabolism. If you ask a clinician, who cares? Let's use hammer. But I will say this is not exactly the mentality I live with inside of an orthopedics department where they're my colleagues next door, but it is kind of a little bit true. But anyway, so again, there's a little bit two different cultures trying to interact here a little bit. They come up with some pretty sophisticated modeling techniques. You pretty quickly come up with a bunch of parameters you have to find numbers for, and you can kind of lean a little bit on history, but otherwise you're in the process of trying to generate those numbers. Obviously, I think if Amir's workflow, this might look a little bit like some of what he showed yesterday, but now it actually starting to feel like there is a patient-specific methodology that can go all the way from 3D motion capture to modeling in the knee, thereby disproving my theory that we need to use some simplified methodology to do it. But I do think there are challenges in scaling this to hundreds of patients, obviously. And they kind of took this finite element method and kind of went to looking at degradation in the tissue, but also then how diffusion and cell-driven degradation could influence that. And that's really a place where it circles back to our basic biology. So we saw an opportunity here. A talented young PhD student, Jonas, came to Iowa City, spent some time in the cell bio lab to find and applied some of those modeling approaches. And again, without going into the details, really brought some teeth to the problem of the mechanobiology, trying to better understand that. So just to try to wrap up here, I think there are opportunities, osteoarthritis initiative was mentioned. There's also a number of clinical trials that are teeing up these days, and great places where modeling could be ancillary studies. The Arthritis Foundation has a Picasso study looking at metformin, but it's just the first in a pipeline of clinical trials they're planning on looking at. I think there are opportunities for modeling to complement that work and try to speed success. My lessons learned, if you're in, and this is a US perspective, but don't go into this thinking, what can I gain? Don't think of this as a new funding opportunity. Allow time for relationships to grow and find someone you work well with and have fun. So that's just the perspective from Iowa, and I look forward to hearing what others have to share.